welcome back from the coffee break. Prabhat's going to be our second speaker this morning. He leads the data sciences and services, the data analytics and services team at NERSC, and interesting diversity and background, doing his computer science at IIT in India, and then master's at Brown, and now doing his PhD in planetary sciences at UC Berkeley. So getting both the computer science side and the science side. So welcome, Prabhat. Thanks.
Cool. Thank you, Steve. Thanks for the invitation. This is my first time at XLDB, and I'm certainly looking forward to the rest of the workshop. So, as was mentioned earlier, the world of science has somewhat been a little late to the streaming real-time data analytics party. And what in this talk, what I'll try to do is to give you a 30,000-foot view of how science is changing and why real-time data analytics and why streaming is more applicable than ever. But first, in order to do that, I sort of need to bring you up to speed on what NERSC is, what Berkeley Lab does, and so on. So Berkeley Lab is about 1 hour north of here. So we're right next to UC Berkeley, which is perhaps our more famous peer institution. Just as SLAC is known for the linear coherent light source, much of the history of Berkeley Lab revolves around the advanced light source. So that's our landmark building. NERSC recently moved into a new facility right on the hill. So this is Wang Hall. And we are a supercomputing center fundamentally. And right now we have a number of petascale class systems, and we'll be hosting pre-exascale class systems at this, in this great facility. Again, SLAC is a DOE lab. Most of you probably know this, but nevertheless, DOE is the largest funder of physical science research in the US. And NERSC is the production HPC and data facility. We support all major applied science offices. When it comes to computer science, historically, simulations is what we've done really, really well. So we know all about high-performance computing. We know how to solve big systems of equations on large petascale class systems. Under the NSCI, so again, petascale is a mission that DOE has owned. Under the NSCI, exascale is the mission that again, the DOE will own. So we know how to run big supercomputers. NERSC cares a lot about science. Our focus is not to make money. We are federally funded. What we care about is science impact. So every year, thousands of users use our machines to publish a lot of high quality science, so a lot of front cover articles on major journals. One of the things which is unique about NERSC, perhaps in contrast to other supercomputing centers in the DOE, is that we have a lot of users. So we have about 6,000 users that represent over 750 different projects. So I think a lot of the challenges that we see in data science applied to scientific problems are pretty much state of the art. We know what's happening in the DOE and the scientific world more generally. So circa 2016, this is what NERSC looks like. At any point in time, we tend to have 2 major supercomputing platforms on the floor. So Cori, the Cray XT40 system, is our bigger machine, which is on the floor right now. And Edison is a Cray XT30 system. You'll note that both of these systems are petaflop class systems. So thousands of nodes, hundreds of terabytes of memory. So again, if you were in the HPC world, you'd be happy here getting these big systems set up, and as long as you connect them to reasonable I/O subsystems, which for us tends to be Lustre file systems. So for Cori, we have a 28 petabyte size Lustre file system. I think you'd be fine. You'd be happy. So one can of course think of the simulation running on a big HPC machine as a source of data, and historically that's how we've treated this. The file systems they've lagged behind in terms of, I think the rates for the CPU power that we have and memory, the I/O system has certainly fallen behind a little bit. But nevertheless, we try and do our best. So right now, setting up pools of shared SSD memory is the best that we can do. So we are experimenting with burst buffer technology, and we've deployed a 1.5 petabyte size burst buffer that can have reasonably high, so 1.5 terabytes a second I/O rates. So anyway, if this big supercomputer was the source of data, you'd be okay. But increasingly, as I'll show you next, what's happening is that the source of data actually resides outside the supercomputing center. So getting the data to the big machine and analyzing it is quite key. So again, one of the unique things that we have in the DOE complex and at Berkeley Lab is the Energy Sciences Network. So this is a dedicated network purely for science. And they have been deploying a 10 gigabit link over the last many years, but they have now prototyped and deployed 100 gigabit networking technology. So ESNet essentially provides a backbone over which a lot of scientific data moves within the US. So essentially, when we talk about real-time streaming and data analytics, data is typically flowing in through the ESNet. There is typically a data transfer node, and then data comes to a machine like Cori, and then we do analytics on it. So historically, we've struggled, I think, a little bit in determining what our hardware strategy should be. We've had big supercomputers for HPC workloads, but when the question came up regarding data-centric workloads, we've fiddled with setting up smaller clusters. But going forward, our strategy is to go for a unified architecture. So a single machine that can handle both HPC and data-centric workloads. So with Cori, we are sort of taking a stance that this XC40 machine, reasonably configured with the right batch policies and configurations and so on, will do a good job at supporting data-centric workloads. Phase 1 of this machine is online now. Phase 2 is expected to be operational later this year. And this will be one of the largest KNL Knights Landing deployments in open science. So that's a lot of background around NERSC. Hopefully you have a sense for the scale of operations that we do. So I wanted to give you a sense for, again, how the world of science and data-intensive science is changing. So I use climate as a surrogate for HPC class applications. What is happening for us, I think, and this is true across all major DOE facilities, is that we are facing a data deluge that originates from experimental and observational sources. So in the field of genomics, facilities like the Joint Genome Institute have a lot of sequencers that stream data to NERSC. In the field of astronomy, people use telescopes of various flavors, high energy physics and light sources. So again, the linear coherent light source here at SLAC is a classic example of a light source that can produce a lot of data. So increasingly, scientists don't just rely on simulations to understand, model and understand natural phenomena, but they use other modalities to understand what might be going on. So I wanted to walk you through a visual gallery of various instruments that are operational at this point in time and produce interesting science. So in the field of astronomy, again, the Palomar Transient Factory is online and has been used for a number of years. The Sloan Digital Sky Survey has been the workhorse for astronomy for over the last decade. And we are participating in something called the Dark Energy Spectroscopic Instrument. All of these instruments can produce tens of gigabytes of data every night. But going forward, the LSST, the Large Scale Synoptic Telescope, will produce tens of terabytes every night. So over the lifetime of the project, you might be looking at data archives that might be tens of petabytes in size. The light source, as I mentioned at Berkeley Lab, if you sort of remove the roof and look inside, it is an electromagnet. So a number of particles get accelerated in this. And the interesting thing, of course, is the tremendous amount of beamlines, specialized beamlines that are set up tangentially to the light source. So entire careers are made on developing custom instrumentation and developing algorithms that can process data. So this, just to give you a sense of orientation, so you might have high energy particles streaming in, you place a sample, it could be a material or a biological specimen, and then there might be a robotic gantry that slowly rotates the sample, and there might be a computer next to this which is acquiring images. So maybe 5 or 6 years back, the modus operandi for some a device like this was a scientist would get a shot at the beamline, maybe for a few hours in 3 or 6 months. They set up the sample, they switch on. Well, the beamline is always on, but the beamline's on. You collect all of these images, and then you take your data, you put it in a USB stick, and then you go home. It might take you several weeks to process the data, to reconstruct the 3D volume. If you find out in a post hoc fashion that something was wrong with your experimental setup, too bad. You need to wait for 3 or 6 more months to get your next time at the beamline. So anyway, so this is how the beamlines were, at least at the advanced light source, were operating so far. And I'll comment more on how we're introducing real-time analytics into operations of this type to help increase productivity of scientists. The Joint Genome Institute has now arrays of sequencers. So the NERSC has a strategic collaboration with the JGI, and every week around terabytes of data are automatically sequenced, migrated to NERSC, and then standard canned pipelines are run to do the sequencing and assembly. In the world of high energy physics, again, these projects tend to be large-scale, massive international collaborations. This is a picture of the Diabei project, which is installed in China. So you might have a tank with a certain liquid. You might have several arrays of sensors that are immersed in the tank. If you look inside these sensors, you see that these are actually lined up with exquisite devices that are capable of nanosecond level. I mean, they have that kind of precision to detect particles that might stream through the tank and perhaps react in this chamber. So over the lifetime of such projects, you might end up with 200, 300 terabytes of data. And at NERSC, we do have several of these data sets right now. Now, the grandest project, I think it'd be fair to say at this point in time in science, is the Large Hadron Collider. Very often, computer scientists get all worked about streaming rates and being able to handle data sets. And the LHC in its raw data rate produces around a petabyte a second. The high luminosity mode experiments, which are about to be conducted for the LHC, can produce 10 petabytes a second. So again, if you're a computer scientist, you're welcome to take that challenge on. But in the meantime, of course, physicists had to get something working. So essentially what they do is they encode pattern detection logic in FPGAs around these detectors, which reduce the data volume by 6 orders of magnitude. You get it down to a gigabyte a second, and then you stream it off. Even then, over several years of operation, the LHC, the worldwide data sets that we have for the LHC are several petabytes. So so that's just a flavor of the kinds of instruments that we have in science broadly. In the industry, I think the 5 V's of data is often used as a mechanism to explain the complexity of this landscape. So I've taken a shot at enumerating the 4 V's of scientific data. Again, the 5th V pertaining to value is not quite as applicable to us. In the industry, it's around monetizing user behavior. For us, I guess we indulge in more altruistic pursuits. So going back to the 4 V's, variety, hopefully you have a sense for how we image natural phenomena in using a range of different instruments. So perhaps for astronomy, you might have multiple telescopes that are looking at the same sky, and you might be imaging in different bands, and so on. The volume aspect, again, I think in a place like DOE, I don't think tens to hundreds of terabytes is something new for us. When we've run simulations on petascale class machines, those are data volumes that we know how to handle. The stack looks a little different in the DOE than it does in the industry, but I think this is something that we can work with. Certainly when data sets start getting into the petabytes or tens of petabytes, then that is a challenge that I think it does become an infrastructure challenge on our side. Our file systems are not necessarily that large so that one user can take over the entire machine and run petabytes and analyze petabytes of data for weeks on end. That's typically impractical. I think the velocity and the veracity aspects are relatively new, and this is what's so the rest of the presentation is going to be touching on these aspects. So the velocity aspect, essentially, if your source of data is going to be outside the big supercomputing center, you do have to pay attention to end-to-end issues. You do have to pay attention to the network that's in between the two facilities, and how do we support a data stream efficiently. So it may be particularly challenging if you have a telescope that's in a desert in Chile, or there might be another telescope that's using a satellite to get the data stream to you. But nevertheless, I think a lot of thought is going into when we deploy instruments like the LSST, are we going to do some processing in situ, and then how do we move the data to the NCSA or other locations. Light sources tend to be relatively close. Again, the advanced light source is on the same hill as Berkeley Lab. The LCLS is right here, and you have in-situ storage capabilities and some smaller scale in-situ computing. But potentially, by using the ESNet, you can get a fairly high-speed network. You can get that light source connected to a big supercomputing center. So anyway, so that's those are some examples of the velocity aspect. The veracity aspect, again, I think the field of data science and big data has to a first order, evolved independently of the DOE and I would say the rest of science. The reason why the DOE and places like NERSC care about machine learning and statistics is because anytime you take a real observation, let's say you're looking at the sky and you have a CCD sensor, you have photons that land on your sensor. So you might have arrays of photon counts, and the question essentially you want to ask is, well, I have these observations, but what was I looking at? So the kinds of problems that we are now starting to look at are inferential in nature. Given observations, tell me what's in nature. And fundamentally, the discipline that is well suited for solving inferential problems is statistics. If you have observations in front of you and you want to search for patterns, the discipline that can help you is machine learning. So I think these two disciplines, stat and machine learning, which of course have seen tremendous progress independently in the industry over the last 5 years, are now becoming really important for DOE as we become more and more experimental and observation-driven in nature. So I think we are starting to look at certainly principal statistical techniques that can work at scale, but certainly methods like deep learning and other machine learning techniques that seem to be doing really well in the industry. All right, so coming to the theme of this session and real-time analytics, HPC machines have largely been these insular things that could not see outside. So if you were on a compute node, you had no notion for the rest of the world. And if you were outside, on a node outside, might be a laptop and whatnot, you could not get into the system. Things were extremely restrictive in the past on HPC machines, so there's only a certain Linux kernel that would run on these Cray machines. But we see that things have to change. Chances are that if you are running on a node, you will need to reach the rest of the world and maybe pull down some data from an external database. If you are running on a laptop or have an IPython notebook or some other interface, you do want to submit a job that actually runs on a compute node. In terms of the OS that's running on these nodes, we do understand that in the world of data science, you hear about all of these stacks. Some of the stacks were touched upon in the last slide. There's just an amazingly rich ecosystem of technologies in data science. So we now have Docker capabilities so that you can boot up custom analytics stacks on your compute nodes, and then users can use that while doing analytics. So anyway, those are all some changes that we are trying to make conventional HPC machines more friendly for data users. So while real-time analytics, chances are that if you are at a beamline, again, you get a few hours on a beamline, and you get that shot once every 6 months. These instruments will produce large data streams, but if I'm going to rely on real-time analytics or some remote capability, fast response time and also predictable response time is absolutely critical. That supercomputing center had better be online when I start acquiring my data. Traditionally, again, HPC systems have been very much batch-oriented. So you configure your simulation deck, you submit your job, and then maybe in 3 days you'll be done. This is not how real-time analytics will work. If people are at the beamline, then they will expect to see more responsive turnaround time. The idea of computational steering has been kicked around for a very long time, and I don't think it's really picked up. The idea essentially is there is a long-running simulation that maybe runs for 3 or 4 days, but you'd like to change parameters in that simulation so that it can, quote-unquote, do the right thing. I think the notion of experimental steering is perhaps more applicable and something that we see people wanting to do. So suppose there is a certain material that you put on your beamline. You have to make choices regarding what temperature and pressure conditions you want to set for that material. You shoot your laser beam or some other beam through. You collect images. You do a reconstruction, And then if on the fly you want to change some temperature or pressure condition, again, if I could look at the results of my 3D reconstruction as I do the experiment, that certainly lets you explore and perhaps understand the scientific phenomena much, much better than the earlier mode where I described, where people take a USB stick and go back to their labs and do the reconstruction in a post hoc fashion. Also, in some cases that we see in science, follow-on analysis might have a time-critical component to it. So one of the things that at Berkeley Lab and a few other folks, in a few other places we've been using is essentially looking at supernova to determine the age and the rate of expansion of the universe. Supernovas, at least in the spectra that we scan, last for a very short period of time. There's a 2-week window in which, from the onset of the explosion, you have a period of 2 weeks to point your telescope, and after that, you won't really get valuable data. So if you can catch these explosions automatically and as soon as possible point arrays of different telescopes at the supernova location in the sky, then possibly you can get more accurate measurements. Folks in NASA, of course, care about asteroid detection, so we have the Near-Earth Asteroid Tracking Program. There's a range of objects in the asteroid belt, but also in the outer solar system. So being able to quickly detect what asteroid might be on a collision course with Earth is important. And again, the sooner you can pick these out, the better. All right, so these are some of the use cases that we have right now running at NERSC. So real-time interaction, and again, I guess Steve mentioned that everyone uses a different word. Well, I think our criteria or definition for real-time is all over the place. I used to work in real-time graphics a while back, and for me it was 30 milliseconds. We had to render the frame in 30 milliseconds. But no, the definitions I think are a little more relaxed. So I would say that order minutes is what we mean when we talk about real-time analytics at a place like NERSC. So interacting with your experimental facility, so we might have, again, light sources. The advanced light source is one example. The LCLS here at SLAC is another example. You might have jobs that are being directly driven by web portals. So again, interacting with the batch system through a bash shell may not be intuitive or appealing to the broad range of sciences. So we now have web portals, again, Jupyter notebooks and otherwise, through which we can submit jobs. And the folks who are developing codes in their web portals or notebooks they don't really have a sense for what the batch system might look like. So I think that's a plus. Computation steering, I think we do see some cases where people who are designing plasma reactors run an ensemble of simulations in the background on a place like NERSC, and they would like to determine what the right control parameters might be that might stabilize plasma. And I talked briefly about experimental steering, which is these follow-on studies where you detect candidates and then you have a step for alerting the worldwide community that we've seen something, an interesting transient, and now let's coordinate and point our telescopes. So I'll get to some of these use cases shortly with some images. So what we are doing in particular at NERSC right now to support real-time computing is to make a small pool of nodes available in a dedicated fashion with immediate turnaround. And again, these words are a little loose. So at this point in time, we set aside about 32 nodes in this particular real-time queue. And this queue has the highest priority compared to a range of other debug and interactive and queues of other scales. And depending on what the demand is, we can expand the size of this queue. Now, because we have so many users, about 6,000 users continuously beating up on our system, and our systems are about 97 or 98% occupied, folks find interesting ways to use and, I guess, abuse the real-time queue. So we do have to be a little cautious about the kinds of jobs that actually want a real-time queue as opposed to the real-time queue becoming a surrogate for getting faster debug jobs through. So anyway, so we've thought a little bit about the kinds of policies that we want to enforce so that our users use it for the right reasons. So there are a range of projects right now that are using the real-time queue, and they span many different science areas. Areas in material science, in accelerator science, astrophysics, biosciences, and so on. I think it's just been a period of about 4 or 5 months that we've been starting to experiment with real-time queues, and almost certainly things will change. I think the amount of resources that we provide to our users and the way in which our users use these queues will almost certainly change with time. So just to again walk you through some specific use cases, the Palomar Transient Factory has been using this mode for actually much longer than 4 months. I think this is one of the more innovative projects that has understood the value of essentially having a static, deep database, which is a deep reference image of objects in the sky. On a nightly basis, new images come in, and then you essentially do a subtraction of this new image compared to the reference image. If you see some differences, then those are likely transient candidates. And then we essentially bring in machine learning technology, and we apply a classifier logic to figure out if this is a supernova versus an asteroid versus some other object. So typically we can, in about 5 minutes or so, determine what type of transient was observed by the PTF pipeline. Once that decision is made, then through cell phones and other mechanisms, astronomers worldwide are alerted to the presence of that transient, and then people essentially coordinate and reach a decision on which telescope around the world will do a follow-up study on the transient object. So we have found in the past several supernova fairly at an early point in their explosion, and we've done a number of high-impact studies on collecting spectra and studying these supernova candidates. For the advanced light source, essentially, as I was mentioning earlier, you have a beamline, you mount a sample, you collect images, so a sequence of images, and then what we do is we run the reconstruction algorithm, so going from images to a 3D volume. We run that on Cori. So this volume is essentially then visualized through a web front end, which is, of course, available to the beamline scientist. So now the beamline scientist, instead of relying on this USB, well, crossing their fingers, assuming that everything in their experiment has gone well, can instead bring up this front end, examine the 3D structure that of their material, and if they need to place another specimen or change some experimental configuration, some experimental parameter, then they can do that in a relatively straightforward fashion. I would say that this has been fairly successful over the last 4 or 5 months. This is running 24/7 now and supporting the advanced light source. There are 3 beamlines at the ALS that use this at this point. And we've certainly stored around a petabyte of data, and several jobs have run the analysis, and we use the real-time visualization capabilities in a fairly routine fashion. So I think this has definitely, I would say, been a game changer for the ALS in improving the productivity of, right now, again, 3 beamlines have adopted this framework, but going forward, we have 23 or so beamlines. So I think we are quite hopeful that this will catch on. Metabolites, so in this particular project, you essentially have, you take a specimen, you use a laser pulse, you ablate the sample, you pass it through a mass spectroscope, and now you have a reading of the mass spectra of a biological specimen. And the question is, well, what exactly was, what is the chemical composition of the biological specimen? So the way in which we are using real-time analytics in this particular context is that we pre-compute. So in the last talk, we heard about computation of a very different flavor. So in this case, we pre-compute various spectra. So we take a large number of compounds, establish what the spectra might be for these pure compounds, and then given a new composite spectra that might be a superposition of new spectra, we run it by this existing database and obtain possible matches. So again, a process that was sometimes done by hand and almost certainly inefficiently can now be done in minutes. And again, I think this, this issue of how do we make HPC resources more easy to use, more accessible for scientists, these are all biologists. So these are all biologists who look at spectra. And most of their expertise is in preparing biological specimens and setting up these experiments. So they really love Python. And again, having an IPython-like interface for transparently using an HPC resource in the backend is really appealing to them. So, a lab with 20 or so postdocs and grad students routinely uses this now. But I think I see this trend catching on. I think as long as we can make these productive interfaces to HPC resources available broadly, then certainly there is an opportunity for the community to share notebooks with each other, but also improve their productivity going forward. From another different biology lab where we look at cryo-electron imaging, we've been collecting image stacks that are on the sizes of 10 to hundreds of gigabytes. And then again, we can do the structure reconstruction on a system like Cori. And again, this theme of assessing the data quality as your data set is being acquired. If there is something wrong, then you, again, can dynamically change and fix the issue. Has been used, I think, fairly effectively for this lab. So closer to home here at SLAC and the LCLS instrument in particular, there is a strategic collaboration right now in place between SLAC and NERSC. And again, ESNet is the intermediary. So again, historically, there have been several pipelines that have been designed and operated at SLAC, where data is acquired on the LCLS and stored locally, and I think in the past even computing has been done locally. But now we are exploring streaming the data using a custom format called XGC, I think, and streaming the data to a system like Cori or Edison, wherein one data stream lands on a high-performance file system, but then another stream might invoke a pipeline. So I think compared to, again, the earlier talk, and I suspect what we'll see from the industry, there are standard entities, standard stacks which are in place. I think things are still in a, in a relatively disorganized fashion, I think, in science. Everyone develops their own workflow, everyone develops their own technology. At this point in time, Pisana is a local tool that was developed at SLAC, and we have this workflow running on NERSC systems, and we are able to run it through a series of operations and produce the reconstruction. I think things got really interesting in the LCLS2 timeframe. That's the big instrument that's going to come online shortly at SLAC, where the data volumes are going to increase by 2 to 3 orders of magnitude. And finally, the networking people will have something to justify a terabit per second network, I guess. So there's going to be a massive data pulse from LCLS2 that will almost certainly require an HPC resource. And I think this is a question which facilities throughout the DOE complex and even otherwise will have to think about. If you're going to spend hundreds and millions and billions of dollars producing these fancy instruments that can produce a lot of data, are you going to co-locate an HPC center next to these facilities? So I think we are experimenting with the super facility concept, which is there's a place like NERSC, which already has these stacks and well-optimized file systems and is well connected via ESNet. Is it possible for us to couple in remote facilities like LCLS2 and others in the DOE complex and do the processing at a place like NERSC? So that's the plan right now for LCLS2. We are actively looking at, again, all the work that we've done for LCLS will hopefully migrate over to LCLS2, and we'll look at a variety of interesting science that is, of course, only going to be possible because of the amazing characteristics of this light source. So I guess we've thrown in the word quasi-real-time here, and in this case, I think if you can get something to the scientists in less than 10 minutes, that will still be valuable to them. And almost certainly, for this data set size, we will need petascale class systems. All right, so a few takeaways. Hopefully, you have a sense for the breadth of activities that we are conducting. So a few takeaways. Data streaming and real-time analytics are emerging requirements in DOE. I wouldn't say that was the case maybe 3 or 4 years back. But again, because the nature of science is changing to become more data-driven in nature, and the sources of these data sets are not, it's no longer just the HPC supercomputer, but it's telescopes. I mean, it's geographically distributed sources. That I think it's time that we thought about how do we stream data to facilities, and then to the extent that the scientist needs it, provide them with real-time analytics capabilities. At this point in time, I think the facilities that have been most successful in coupling with NERSC and getting their science done are in the area of light sources, the advanced light source and the LCLS here, but also a few telescopes in the astronomy community. Technically, Sdn Software-Defined Networking is something that we are looking at. There are complicated end-to-end issues having to do with provisioning. You need to make sure that resources are allocated. So in conjunction with your time on the beamline, you need to make sure that the network is provisioned, the compute resources are provisioned at a remote facility, the credentials that you have on a local machine, in a place like SLAC will actually carry over to a place like NERSC. So anyway, so there are a bunch of provisioning issues, but once the provisioning issues are taken care of, guaranteeing throughput is going to be key, and we think that SDN might be a critical technology going forward. Certainly, I think our users push us in interesting ways, and again, determining the right policies to enforce the intent of the real-time queue is an ongoing challenge. And again, this is an area in flux. So I think is 32 nodes enough? Do we need to provision 1/10 of our supercomputer? Do we need to provision a half of it? Almost certainly, our utilization metrics will fall. Again, users use our machines at the 97, 98% level. And if we over-provision, that could be an issue. So this is something which is an ongoing debate internally at NERSC. But I think it's really quite exciting to see how people have been using such capabilities in production. All right, so I just want to thank folks who did the actual work and provided me material for this slide, and that's it.